So yesterday I've explained you basic machinery of heights within Arithmetic geometry. I mean, a notion of height of subvarieties and using miniaturized line models. And the last slide was devoted to the theorem of Chauvin's, claiming that for, let's say, a polarized dynamical system, the analog of Bogomonov's conjecture is true if and only if the height zero subvarieties are precisely the preperiodic subvarieties. And as I said, this theorem is related to a close interaction between heights of points and heights of subvarieties, which has been established by Chauvin, and which I want to show you in the next part. So this is called arithmetic positivity. And before I can discuss arithmetic analog, I have to go back to the geometric one. So in the geometric case, we have fibrations over a curve and a line model on the total space of the fibration. Now, what does it mean that well, the analog of the relation between heights is the fact that if a section has positive degree, a section of this fibration has positive degree against L, then this is related, so this fact is related to the existence of global sections for the line model L. Of course, if I have a global section S which does not vanish identically and which does not vanish, well, such that the point P, which does not vanish at the point P, then I can, to compute the degree of sigma P with respect to L, I can use the divisor of this section. And since the section sigma P is not contained in this divisor, the degree is just computed by computing local intersection multiplicities, and they are positive, well, they are non-negative because the cycles are in good position. And so you get the fact that the height is non-negative. Conversely, but now we want to understand the converse. So if the line model is ample, at least on the generic fiber, then the line model, or its powers, but it's the same for the moment, well, it does not change, does not make any difference. Then, so the line model will have global sections. And the divisor of, so for the moment, it's just global sections. So I have X over B, and I have the generic fiber. And here I have some line model L. And so I'm just talking about section of L on the generic fiber. Such a section has a divisor here. And the divisor extends. I can take the Zariski closure in X. And so I can extend the, no, I don't do that. I look at S as a meromorphic. I don't take the Zariski closure for. I first consider the section as a meromorphic section of the line model L on the variety curly X, and then I look at this divisor, so divisor of the section S on X. So this divisor has two parts. One is horizontal, which means that it projects onto B. And this part is the Zariski closure of D. Can you read here? Yes? No? Okay, so. So you have divisor on X of S as one part which is the closure of D, plus some vertical part, meaning that it is contained in fibers. And let's say, assume that the whole fiber is in the divisor of S, appears in the divisor of S with coefficient D. Then this means that the order of this section will vanish, well, the order of this section with respect to the t-adic valuation will be at least D for any point which is not contained in the divisor S, in the divisor of S. And this inequality is equivalent to the fact that the t-adic norm of the section S is smaller than exponential minus D at the point P. So the conclusion is that if the inequality norm of S, the t-adic norm of S is at most T for all T, then the section S will extend to a global section because it won't, the divisor of S won't have any vertical components. Well, this holds at least if the space is normal because otherwise codimensional subvarieties don't detect integrality. But basically, this is what happens. So to detect the fact that a generic section on the generic fiber is integral, it means that it has norm smaller than 1. Okay, and if it extends to a global section, sorry, I don't know why. So if it extends to a global section, then I will have positivity for height of points outside of the divisor. So I want to do the same in arithmetic geometry. So I let X be a variety of a number field, F. I take a line bundle together with a metric. And I define one space and two numbers. So the first space is denoted H0 of X L bar. So this is a space of arithmetic global sections of the line bundle, of the metrized line bundle L bar. So this is the analog of H0 of curly XL. So I define this space as the space of global sections of the generic fiber, which have norm at most 1 at all places. So this is exactly the analog of H0 of curly X B, as I explained in the preceding slide. So now this is a finite set, usually, and I will define small h0 of x L bar to be the logarithm of the cardinality of this set. And so this is the number which I am interested in because I want to find section. If I'm interested in the positivity of height of points, I'm interested in such sections which have absolute value, which have norm smaller than 1 at all places. So I'm really interested in this small h0. But this number is hard to understand. So a better number, which is well behaved for exact sequences, inductions, and so on, is this chi of xl bar, which is a kind of which is defined as follows. I look at the global section, gamma of xl. So this is a Q, well, this is a F vector space, but I can tensor it with R. So I get a R vector space. And within this space, I have two objects of different nature. The first one is the ball at real places, or at Archimedean places. That means the set of sections whose norms are smaller than 1 at all Archimedean places. And the second set is lambda. It's a set of sections who have subnorms smaller than 1 at all finite places. And I'm interested in the intersection of these two sets. So observe that lambda is a lattice in gamma of xl, and that B is a ball, really a ball. So now you see that the set I'm interested in is a set of points of a lattice which belong to a given ball, to the unit ball. And so Minkowski's theorem tells you that this set is related to some numbers, which is precisely the logarithm of the volume of the ball divided by the covolume of the lattice. And so Minkowski's theorem is just on bottom of the slide. It tells you that this H0 is at least the chi of XL, the bar, and you have some error term which is controlled by the rank of the vector space, the dimension of the vector space. Okay? So if I can bound this from below, then I have a lower bound for that, and maybe it can be of some use. So I want to understand the behavior of such numbers, gamma of XL bar. So there is if I go back to algebraic geometry, what I'm interested in, this chi is the analog of the direct image of the line model L on the base B. And so I have a Hilbert-Samuel formula, which tells me that the degree of P Loir star L to the K is approximately 1 over factorial n times the degree of x, that sounds, okay, the degree of the variety curly x with respect to the line model L times k to the n. At least if the line model L is ample, is relatively ample. So this follows from, say, you can prove it from scratch, but you can also prove it using Riemann-Rohr and vanishing theorems. So in arithmetic geometry, there is a similar statement, which is due to Gillet-Soulet, but this, the statement which is on the slide is due to Zhang, because I have no assumptions on regularity and things like that. Essentially a simple derivation from Gillet-Soulet's theorem, and it is false because there is a small k missing here. So it says that this number, chi of x L bar to the k, has an asymptotic expansion, and the leading term is 1 over factorial n plus 1 times C1 hat of L bar to the power n plus 1 against x times k to the n plus 1. So this number is precisely the height of the variety x, as the number above is the degree of the variety curly x. Okay, so the analogy is there, and the n has been changed to n plus 1 because in the geometric setting, see, this curly x was of dimension n, so this means that the generic fiber is of dimension n minus 1, and here I have only the generic fiber. X is a generic fiber in some sense, of some non-existing vibration over some projective arithmetic base. So this theorem has two proofs. I really can't give a proof of that theorem. So there are at least two proofs in the literature, and maybe some more, but okay, at least two. One is due to Gillet-Soulet and uses the analog of the Riemann-Rohr theorem in Oracle of geometry, combined with estimates on the analytic torsion due to Bismuth and Vassereau. So it's quite difficult. And there is a simpler proof which does not use Riemann-Rohr, and which tries to study directly the space of global sections of subnorm at most 1, which is due to Abbes and Bush. So you have two proofs. One is using Riemann-Rohr and, in some sense, vanishing theorems, as you try to bound cohomology and analytic torsion, which is the analytic analog of cohomology at finite places in that context. And the other more or less follows the classical proof of Hilbert-Samuel formula. And needs also a lot of analytic inputs, but nevertheless, it's simpler. So if you combine both theorems, Minkowski and Hilbert-Samuel, then you get the following result. Assume that L bar is semi-positive, which is this vertical, an analog of vertical impedance, and assume that the height of the variety x is positive. Then you will find many sections for powers of L bar, which have then this number will be big when k goes to infinity. So chi will be big, and if chi is big, then h naught is big too, because the difference of chi and h naught is controlled by the dimension of the space of global section, and this dimension of the space of global section is given by the Hilbert-Samuel formula. It's something like k to the n. So this is really the leading term for chi and for h naught. So if the height is positive, then you will find arithmetic global sections. And then you can use these sections to compute the height. This formula is just that if you take a point P, which is not in the divisor of S, then the height is just the sum of minus log of norm of S at all places P. And you will see that this height is non-negative. Okay? So this is the simplest. This is the simple part of this positivity, this relation of heights of points and heights of varieties, which I will use in the equidistribution theorem. But there is a harder and converse inequality in the other side, which is also due to Zhang, which says that if the height of points is positive, then the height of the variety will be positive. And so the easy side is related to Hilbert-Samuel, and the hard side is related to a Nakai-Moishezon theorem in arithmetic geometry. So you need a criterion for a line model to be ample in arithmetic geometry. So now, what one can do, it is unlikely that my given line model will give a positive height to the variety. Let's say, because if I look at a polarized dynamical system, then the height of the variety is 0, as I explained, because the variety itself is preperiodic. So the hypothesis that the height is positive is not satisfied in practice, but what I can do is I can rescale the metric. I can multiply the metric by any fixed number, and then I can compute the new height of the variety, and for some values of the scaling, the height will be positive. So for that values of the scaling, I will get positivity of height, and then you can see what happens in practice. And so the result you get is that if you take an ample line bundle with a semi-positive metric, and if you take any sequence of points, pk, which is generic in the sense that it is not, no subsequence is contained in the subvariety. I have to avoid any variety which is fixed in advance. Then the height of the points, there is some hand which should not be there. The height of the points pk will be bounded from below, at least in the limit, by the expression on the right-hand side, which is the height of the variety, x, divided by the degree of the variety, and there is a small factor n plus 1. So this tells you that if the height is non-negative, then if the height of the variety is non-negative, except on some closed subsets, the height will be maybe not non-negative, but greater than so it will be at least some minus of some epsilon, which is as small as you want. Okay? And what happens about equidistribution theory, when equidistribution theorems appear, is that if you find a sequence of points pk such that you have equality here in this formula, then this sequence will provide you equidistribution, will be equidistributed. So, to explain that, so equidistribution is related to a variational principle in Arakelov geometry. I mean, it means I will study the preceding inequality, not only for the line model L bar with its matrix, but for small deformations of this line model. So, and this equidistribution was first observed by Spiro, Ulmo, and Zhang in their work on when they worked on abelian varieties. So there they observed this equidistribution phenomenon, and so their proof was maybe only given for varieties, but it was for abelian varieties, but it was clear that it extended to something fairly general. And the idea for the proof, though, is to apply Zhang's inequality to small perturbations of the line model L bar. So you pick up a function phi on x, on the complex space of x, because you're interested in complex equidistribution. And you denote by L bar of epsilon f. Epsilon phi, it's not a f, it's not a phi, it's a f. The metrized line model, which is obtained from L bar by multiplying the metric by exponential of minus epsilon f of phi. Okay, so it means that if the norm of a section at a point if the norm of a section at a point was norm s of x, at the new point is norm s of x multiplied by exponential minus epsilon phi of x. Just means that. And now you can compute how the heights of points and varieties are modified in that modification. So for the height of point, what you get exactly is that the height gets, you have a new term to be added, which is epsilon times the sum of the function phi at all conjugates of the point p. And you have to divide by the degree of p. And so what you add is exactly epsilon times the integral of the function phi against this discrete measure delta of p. Because delta of p is just 1 over degree of p times the sum of the Dirac measure at the point PG, or PG or conjugates. So this is what you get for the height of the point P, and for the height of the variety X, then you can use multilinearity of the height pairing and see what happens. So you get the first term. The first term is, of course, the height of X, because when epsilon is 0, then you get the initial metric and you get the height of X. So, and the first term is n plus 1 times epsilon times the integral over the variety X of C of the function phi integrated against the measure C1 of L bar dim X. You remember that to L bar I had attached, let's say in the case of elementary grand functions, I had to attach a curvature form and then could take the power, maximal power of this curvature form to get a measure. Okay, so this measure appears exactly in that formula. So now what I can do is take a generic sequence of points and look what happens. So I will take, I'm interested in the distribution of such measures here, so delta of the pk. So I will take a measure nu on the variety X of C, which is a limit which is a limit of those measures, and I will try to see what I can deduce on this measure nu from Zhang's inequality. So first of all, the infimum limit of h of pk is just by the formula for the height of points, the infimum limit of the height of pk for the old line model plus epsilon times the integral of phi against nu. So now what is the infimum limit of the height of pk? By assumption, it's just the height of x divided by n plus 1 degree of x, because I assume that the sequence pk was achieving equality in Zhang's inequality. And there is and the second term is just epsilon integral of x of c phi nu. I have rewritten phi nu. What did I say? No, it's written completely. It's not, sorry. So I have to. So what I said is the infimum limit h L bar of epsilon phi for pk on one side is equal to infimum limit h L bar of pk plus epsilon integral of phi nu. On the other side, it's at least equal to, by Zhang's inequality, to h L bar of epsilon phi of x divided by n plus 1 degree of x. So on the denominator, the degree does not change because I've not changed the line models. The line model, I've only changed the metric, so this does not change. And so this is equal to h L bar of x plus n plus 1 epsilon integral of phi c1 of L bar to the power time x plus some error term, which is small, divided by n plus 1 degree. So now this is this term is at least equals to that. So you see that this and this cancel. And so you get that epsilon times integral of phi nu is at least epsilon times integral of phi against C1 of L bar divided by degree of x to the power time x. Okay? So now this is a plus some big O of epsilon squared. So now I can get epsilon go to 0. And what happens is that this gets at least that if epsilon goes to 0 by using positive values. But if I use negative values, then I get the other inequality. So the limit, so that is equals to. And this is exactly what I wanted to prove. That is, I have taken a measure nu, which is a limit of this sequence of measure, and I've shown that this measure nu is precisely equal to the measure attached to L bar. So now, skip the beginning of the slide. So by compactness of the space of probability measures, there is only one limit value. So this sequence of measures, delta of pk, has only one possible limit value. And by compactness of the space of measures on a compact monometrizable space, and this implies that the sequence delta of pk converges to this limit value. Okay? But nevertheless, there is some assumption which is necessary for all of that to hold, is that I needed to use Zhang's inequality here for this line model L bar of epsilon phi. So here I use Zhang's inequality. And for Zhang inequality to hold, I need that the line model L bar of epsilon phi is semi-positive, at least if epsilon is small enough. And this was, and this is a, well, this might not look so, but this is a very strong assumption. So for abelian varieties, it was satisfied because the 1-1 form that one gets in the theory of near-wanted height is exactly the Kähler form on the abelian variety attached to the line model L bar, to the line model L. So it is a Kähler form, it is strictly positive everywhere. And when I deform it by some epsilon phi, I get something which is still positive. And so the positivity assumptions are satisfied. But for dynamical systems, then this measure mu L bar is precisely the canonical measure mu f. This is what I explained on Wednesday. And Berthelot, Dupont, and Loeb have shown that the positivity of this measure mu f is characteristic of examples coming from abelian varieties. It means really that this measure mu f is very singular. It's not at all likely to have a support, to have a high dimensional, a support which is big. And even if the support is big, it's unlikely to be comparable with Lebesgue measure on the support. Unless the dynamical system comes from an abelian variety where you don't need all that because you already know equidistribution by the case of abelian varieties. So it was a major obstacle to, it is a major obstacle to use Zhang's inequality to prove equidistribution for a dynamical system. Anyway, Autissier proved in his thesis in around 2000 that the positivity assumption is not necessary for curves because he could prove an inequality of Hilbert-Samuel type without any positivity assumption. The fact is that for curves you have H1, H0, H1, and H2. And the H2 has a positive sign, so which doesn't matter for that work. And the H1 he could control. So in that way, he could achieve equality. So this implies that if you take a dynamical system on P1, then you have equidistribution of points of small height towards the canonical measure mu f. Okay, so that was the situation until the beginning of this year. And so in March, Shou Zhang told me that one of his students had proven a theorem that allows not to remove the semi-positivity assumption in Zhang's inequality, but at least to circumvent it. So I go back to algebraic geometry to explain what happens. There is what we want to do is to find arithmetic sections of this line model. And this line model is essentially the sum of two line models, two metrized line models, that one and that one, which is a trivial line model equipped with this metric epsilon f. So we want to show that sum of line models have sections. And Hsu proved that if you take two ample line models, L and M, and you look at the difference of them, then the powers of this line bundle will have many global sections when M is not too big. I mean, C1, the degree of L, the degree of C1L to the power n, the maximum power, has to be greater than n times C1M, C1L, and minus 1. So it means that for small m, a difference of an ample line bundle on another one will still have many global sections, at least if I take powers. So I will still have an inequality. And so the analog is due to Zhang's student, Yuan. So if you take two line bundles L bar and M bar, which are arithmetically ample, I don't want to define what it means, then this chi number of the divisor, the metrized line bundle L bar times some M bar minus 1 to the power k, will be at least equal to this term, which looks exactly like Siu's second hand. So second Siu's formula, you see you have the difference of the height and the difference of minus C1 M bar times C1 L bar to the power n, plus some, so times k to the n plus 1, plus some error term, which I won't be. And so this equality allows you to apply this variational principle in general. And so this shows, this concludes the description of the equidistribution theorem for, let's say, dynamical systems. So take a polarized dynamical system of our number field, F, contained in C. Denote by HF and mu F the canonical height and the canonical measure attached to this dynamical system. Take a sequence of points of algebraic points in X of F bar such that first the height go to 0 and second no subvariety contains infinitely many points. Then the discrete measures delta of pk converge to the measure mu F. Okay. So it meant that I've been much quicker than I expected to be, and that we'll have the time to explain you periodic equidistribution now without to bother you at 5 o'clock. So it will probably be better to do that now. So now what about periodic equidistribution? So the question is, well, the question you might expect. You take a prime number, you complete the number field. Well, you complete the field Q with respect to the periodic valuation. You take the algebraic closure of that. You get QP bar, which is not complete, but you complete again. You get CP, which is algebraically closed. You take a variety of our number field F. And now, given an algebraic point on X, you still can define a measure, a discrete measure, on the variety, whatever it means, X of CP. At least it's a variety in the sense of, well, there's notion of soft periodic analytic spaces, well, which we can find a definition in Bourbaki and something like that, which is not very useful in algebraic geometry, but anyway, it does exist. And so you have this topological space, which is analytical, CP analytic variety. And you can use measures on that spaces, and you have discrete measures attached to algebraic point just by averaging the discrete masses, direct masses at all conjugates. Now you take a height function of X, let's say 1 given by a polarized dynamical system.
Are these real valued measures or
Real valued measures. This is real measure theory in any sense. Okay, and the question that you can ask is, what is the periodic limit distribution on the space? How do the measures behave? And so what I discovered is that if you want to answer that question, you have to introduce Berkovich spaces. So Berkovich spaces are a new kind of analytic spaces in the periodic case, which, so I have to refer to explain the new. So if you have a variety of a periodic field, you can look at its p-adic points, and it gives rise to a p-adic analytic variety in the soft sense, which is not interesting for algebraic geometry because it is totally disconnected, so you don't have any Gaga principle and on. So now there have been many, I say not tentatives, but a lot of efforts to define a good notion of p-adic analytic spaces where you would have Gaga theorems, comparison between analytic geometry and algebraic geometry. And one of them is due to Tate, which still looks at this topological space, which is totally disconnected, but it forgets for a moment this topology and introduces a new topology, which is actually not a topology, but a Grothendieck topology, and then in that framework, he is able to study these spaces, and there are many important reasons for those rigid spaces, for example, Gaga theorems in the proper case and so on. But I believe that it's not possible to do topology on those spaces still. So the spaces that Berkovich introduced contain all these p-adic points, but they contain many more points. In some sense, Berkovich added many generic points to this, let's say, naive variety. So these points correspond to multiplicative semi-norms on algebras. So in algebraic geometry, points correspond to morphisms from algebras, from finite type K algebras, or K is a field, to fields. In the Berkovich sense, they correspond to morphisms from affinoid algebras, which Henry described a bit yesterday, to not only fields, because you want to do analysis, but to valued field. And so if you have a map from an algebra to a valued field, then you have a semi-norm on the field, which is given by taking an element of the algebra, pushing it to the field, and then taking its absolute values there. And it's a semi-norm because the map could have a kernel. And so these spaces are quite complicated. For example, if you look at curves, you'll get something like a graph. It looks like a graph in some rough sense, but it is very hairy. I mean, it's a graph which you have a length on the edges, and at any rational point on the edge, you have some graph which is leaving, and on any rational point on this graph, you have branches that spread out. And so it's a hairy space in some sense, but the topology is good enough so that you can do topology or analysis on them. For example, if you take a smooth connected algebraic variety, what you get is locally compact, is path connected, and is even locally contractible by a deep theorem of Berkovich himself. So you get spaces that are closer to the spaces one is used to do analysis with. So I want to describe a bit more detail the unit disk over CP. So in any theory of analytic functions over a disk, one knows what such a function is. It means it has to be an analytic function on the disk, has to be a power series which converges on the disk. Okay, so the functions on the disk has to be the set of formal power series whose coefficients in CP go to 0. It's a closed unit disk, yeah. So, well, there is an important feature of p-adic analytic spaces, which you can find either in Tate's approach or in Berkovich's approach. In approach, that the basic sets you can work with are affinoids, and they look like compact sets, not like open sets.
So if you have an affinoid, you add just one generic point?
No, you'll see. I'll show you. You had many more. So on this space of analytic functions, I have a norm, which is just the maximum of the norms of the coefficients of the analytic function. I take the power series, maximum n. And a theorem of Gauss tells you that this norm is multiplicative. So it's an appropriate place to talk about that. So the unit disk is defined by M of A. So M is the notation of Berkovich. It's a Berkovich spectrum in some sense of A. And it is a set of all multiplicative semi-norms which extends the evaluation of CP. And, well, you have to say that these norms are bounded, but I mean, you only look at norms that are dominated by the norm, the Gauss norm, because otherwise you could get pathological things. So classical points of the disk correspond to the semi-norm F goes to absolute value of f of z. If you take z in the disk, you can evaluate any function f, any function f in A at that point z, and then take the absolute value. It gives you a multiplicative semi-norm. Now you have a new point. You have the Gauss point, because I told you that the Gauss norm is multiplicative, so it gives you a new point of this Berkovich space. And the rest I've said. So at least you have the classical points plus one new point. But so to define a topology, when you just say that if you have a function.
So let me repeat the question. What are the, apart from the classical?
I'll show you. I'll show you in 2 seconds, 2 minutes. So you have to define a topology on that space of norms, and you define the topology as in theory of Gelfand spectrum and so on. So you ask that if you take a function, then you want to evaluate the various norms of the function, u of f, and you ask that this is continuous on the space of norms. Okay? And so the space you get is a compact topological space, and it is also metrizable because the residual field of CP is countable. So the affinoid algebra CP of Z, CPZ has a countable dense subset. So moreover, this space is connected and contractible. And moreover, in that case, you can join any 2 points by a unique injective path. So the example is the following. I show you a path which will go from the 0 point to the Gauss point. And I define nu t to be nu t of a function f, where f is sum of a and z to the n, to be the maximum of absolute value of a n times tn. And this is exactly the supremum of the function f on the disk of center 0 in radius t. And this is multiplicative still by Gauss theorem. Okay, so this gives you a semi-norm. And the mapping, the map which assigns nu t to t is continuous because this function max of a and tn is continuous. So in that way you see that I have drawn a path from the point 0, when t equals 0, you get exactly the classical point 0, to the Gauss point when t equals 1. And so now, so this shows you one path. But why can you, for instance, connect any classical point to any other? Then, in p-adic analysis, disks have many centers. In fact, any point of the disk is a center of the unit disk. So you can do the same construction by using another center, and then you go from 0 to the Gauss point, and then from the Gauss point to any other center. Sorry?
Do
you know that? Well, you can describe it more precisely, and you see that it is unique. But it's not. Est-ce que c'est facile de voir que Is it easy to see that the path is unique? No. That the path linking 2 points is unique. So this is the case for the unit disk, but it's.
So, but the norms that you go through, correct me if I'm wrong, they look like they are Gauss norms of different disks.
Right.
So let me repeat the question. Do you just have one point for each disk? I mean, for each affinoid?
No, and so you have those points. Now you can take a decreasing family of disks. So usually, if the radius of the disk go to 0, then the intersection of the disks will be a single point. But if the radius don't go to 0, then two things can happen. Either the intersection is still a disk, or the intersection is empty. Because CP is not, what is the word? No, it's not a problem of being locally compact. It's a problem, it's spherically complete. It's spherically complete. I mean, intersection of disks, a decreasing intersection of disks is not, might be empty when the radius of the disks doesn't go to 0. So you can check as an exercise in the real numbers, if you, in a real vector space, if you take a decreasing collection of disks, then the intersection is non-empty. But in the periodic case, it's false. It's due to the existence of extension, well, I don't want. Okay, so you have this decreasing collection of disks whose intersection is empty, gives you a new norm because the infimum of all norms, of all subnorms.
But still, for each disk, you have just one.
For a disk, yeah, but in that disk you have new disks, so you have. In fact, each time you get out one of these strange new points, the space gets totally disconnected. It gets disconnected into infinitely many components.
Wait, say that last part again?
Sorry?
What was the last thing you said?
I say that if you, say, remove the Gauss point from the Berkovich unit disk,
Oh, if you remove the Gauss point.
then what happens is that you get a countable collection of open unit disks indexed by the residue field of CP. So you have many open disks that are just linked by one point somewhere. So I will show you the periodic analog of Belo's theorem. So Belo's theorem was the fact that the distribution of points of small Weyl height in the complex projective line was related to the integration measure on the circle. I had said that for, at least if you look at roots of unity, that they could distribute to the integral of the circle, but it's the same for any sequence of points whose height goes to 0. So let's consider a sequence of distinct points in P1 of Q bar whose Weyl height go to 0. And then the sequence mu xn of measures on the analytic space attached to by Berkovich, let's say at the place P, converges to the Dirac measure at the Gauss point. So it means the analog of Belo's theorem, there is a convergence theorem, but the limit measure is a Dirac measure at this new point. So that's why one had to introduce them. So in general, there is a similar theorem, there is a full periodic equidistribution theorem. And to describe it, I have to show you how to define measures.
So wait, what was the original Belo's?
Sorry? Belo's theorem is equidistribution of points of small heights on the projective line when the height is the Weyl height. It is a dynamical system x done x2. Okay. So now, how will you define a measure on a Berkovich space? At first sight, it might appear complicated because on the complex case, we had functions, we could derivate them, and so on. Now we can't. So I first show you what it happens when the variety and the line bundle and the metric on the line bundle is elementary, in the sense that I have embedded the variety in the projective space. The line model is just the O of 1, and the metric is just the usual Weyl metric given by the embedding. So now what can I do is take the Zariski closure of the variety x into the projective space over the integers. I get an integral model of the variety x. Well, I will assume for simplicity that this model is normal, but it's not a serious assumption. And I will look at the spatial fiber of this model. Okay? So the special fiber, in general, might have many irreducible components, and they may have some multiplicities, xj and mg. And one fact, which is implied by the fact that x curly x is assumed to be normal, is that the xj is a reduction of, that there is on the Berkovich space a canonical point, which I call xj, which in some sense reduces to the generic point of the variety xj. So it happens so. If I have a point in some affinoid algebra, say, so semi-norm, nu to r plus, I can look at the kernel of nu. No. What can I have? So I have a subalgebra which is given by, so A is a quotient of the algebra of power series. So I can take the algebra, maybe the quotient of the algebra with integral coefficients. So it's not exactly like that. And this algebra itself has a quotient which is a finite type FP bar algebra. And to the norm nu corresponds its kernel, which is a prime ideal in the algebra A, and then I can intersect it in A naught and look at what it happens at the level of A mod A naught mod A naught naught, and I get a prime ideal here. So I get a point in some algebraic variety. So this is roughly the description of a reduction map from a Berkovich space to some algebraic variety, which is a reduction in some sense of the space. And the variety xj, in that sense, is a reduction of a single point, psi j. So now, I moreover compute the degree of the special fiber, or of the component xj of the special fiber. And the measure is, on the analytic space, is simply defined as the sum over all components of the Dirac measure at the point psi j, multiplied by the multiplicity and the degree. Okay, so these measures are discrete, but their support is contained in the set of new points. These points, xij, do have nothing to see with the classical points. So they are really new points. And this definition is inspired, well, I was inspired by a paper by Kani, who was trying to do a Rakelov geometry in a p-adic context. And he used measures, but he only introduced not sigma additive measures, but finitely additive measures. And what's the name? So the Boolean algebra on which this measure, this finitely additive measure took place was the sets of all affinoids. So when you have an affinoid, you have such points, Cj. And in some sense, his measures can be viewed on the Berkovich space as linear combinations of Dirac measures. And that's why he couldn't use, he could only have finite additivity because he could not sum indefinitely Dirac sums. So I give two examples. The first one example, if you look at the veil height, so the veil height is just given by the standard embedding of P1 in P1. So what is the Zariski closure? It's just P1, you don't do anything. And the special fiber is just P1 over FP bar. And the degree of the line model of 1 is 1. And the point psi, which corresponds to the special fiber, is exactly the Gauss point. So the measure you get is exactly the Dirac measure at the Gauss point. And if you look at polarized dynamical systems, then you will get in a similar way as in a measure on the space, which is similar to what happens. So now this works for elementary metrics, but if you want integrable metrics, any metrics, then you have to go through the limit process that I described and verify that you take elementary metrics converging to your metric, and then you, yes?
So when you have a Dirac measure or such a thing, how do you evaluate the function?
Just take the value of the function at the point.
So the evaluation is the value.
Right. No, if you have a space and a point x on the space, and you want to integrate the Dirac measure of at x against a function phi, which is continuous, and it's just phi of x.
So what's the value of the function?
You're talking about continuous function. You're talking about continuous functions. In measure theory, you're integrating its real valued functions. So they have nothing to do with theta algebras. Okay. So you have to trace the limit process and check that if you go through this process, this discrete measure converges to something, which does not depend on any choice. And this, again, is what makes the thing work is really positivity that one can find anywhere. So that way, I have measure C1 of L bar to the maximal power on these Berkovich analytic spaces. And the properties of these measures are pretty much the same as in the complex case. I mean, the total mass of this measure is the degree of the variety. If the line model is the line model has a semi-positive metric, which means that it's uniform limit of elementary ones, then the measure is positive because it's a limit of positive measures. There is a symmetric multilinear extension. I mean, if I take I can take products of various line models in number equal to the dimension of the variety, and I will get measures. And there is a compatibility with morphisms and products, which is a bit complicated because the product of two Berkovich spaces attached to two varieties is not the space of Berkovich attached to the product, but there are maps and so on. Contrast. So one remark is that I have defined this maximal power of C1 of L bar to the n, which is a measure, and I have no idea at all how to define just the single C1 of L bar. I mean, I can define measures, but not currents. It's life. And so with all these definitions that I have shown you, what happens is that all the variational principle and so on goes exactly through in the periodic context. So one just needed to understand these measures, how to make them live, and then all the machinery from Arithmetic geometry goes through. And so in that way, one gets a following distribution theorem for, let's say, polarized dynamical systems over periodic fields. If you take such a polarized dynamical system and a sequence of points going to 0, and you assume that any subvariety contains only finitely many points, then the discrete measures delta of pk converge to the measure mu f.
Don't you need something like expanding by multilinearity?
Yes, but I am saying that. Yes, but it was the third point. That is multilinear. You can extend it. So without knowing each, but just by polarizing. So there is, at least, there is this essentially verbatim that I could discuss 1 minute. In the complex equidistribution theorem, I had taken some function phi, a test function, to know the limit of the measure, and usually the test function was C infinity function. So on the Berkovich spaces, I have no C infinity function. So what I need to have is enough functions so that I can, testing the measures on them is enough. I mean, this means dense subset of function. And this dense subset of function is given, let's say, by integrable matrix on the trivial line model. I say, say like that. I can, if I write the trivial line model as a difference of two line models, twice the same, line model minus this felt, but I endow the two line models with different semi-positive metrics, then I get a metric on the trivial line model. Then the norm of 1 is some function, which will be continuous by all the definitions. But not any continuous functions can be achieved that way. But these functions, nevertheless, are dense in the sets of all continuous functions. And this is an application of the Stone-Weierstrass theorem on the Berkovich space. And it's a theorem of Gubler that such functions are dense. So in that way, I get a dense set of functions, which is related to Arakelov geometry, and so the process can really go through. And so one gets the proof of such a theorem. Gubler, Walter Gubler. He wrote 2 papers on local heights of varieties, one in Krelle and one in some confondu, Padova, something like that, or Pisa, maybe, I don't know. I don't remember. So, and he introduced also, in some part of his work, there are Berkovich spaces entering the picture. So he proved the density theorem which is required. So I stop here. Thank you very much for the question.